All right, so now we're going to be reviewing some trig identities, and we're also going to be finding derivatives of some trig functions. This is a Pythagorean identity that probably all of you know. Just reviewing why this Pythagorean identity works. If you think back to your unit circle, anytime we have a triangle within this unit circle, this would be x, this would be y. Because it's a unit circle, the radius would be 1. Now, based on the Pythagorean theorem, we would know that x squared plus y squared equals 1. What is x the same as when we're talking about trig? The x value is the same as what? Cosine. So if x is the same as cosine, we can see that if x squared plus y squared has to equal 1, then x is just going to be cosine, so cosine squared theta plus sine squared theta must equal 1. That's where this first Pythagorean identity comes from. Let's say you want to get the other Pythagorean identities. What can I divide through by? I can divide through by anything I want. I can divide through by 2, 3. I can divide through by sine squared theta. So what if I do divide through by sine squared theta? Sine squared over sine squared is 1. Cosine over sine is cotangent. And 1 over sine is cosecant. So this is another Pythagorean identity that you need to know. So jot this one down. 1 plus cotangent squared theta equals cosecant squared theta. So I could divide that through by sine squared. What else could we divide it through by? Cosine squared. So I'm going to come over here and divide by cosine squared. So cosine squared divided by cosine squared is 1 plus sine squared divided by cosine squared is tangent squared. And 1 divided by cosine squared is secant squared. So these are my other two Pythagorean identities. And these are going to be used a lot when I'm doing a trig problem that involves differentiation. I might take the derivative. If I end up getting this as my answer, well, that's not completely simplified. That's the completely simplified answer. Here's some new derivative rules we have to know. The derivative of tangent x. We actually did this on our homework, and you probably didn't even notice. The reason you didn't notice is because this is the way the problem was written. It asked us to find the derivative of sine theta over cosine theta. Well, what is sine over cosine the same as? Tangent. So when we found this derivative, we were really finding the derivative of tangent. Remember what we did here? We used the quotient rule. We did f prime g minus f. G prime was negative sine theta over the denominator squared. Well, what's this going to be? If I have sine squared theta plus cosine squared theta, what is that? Just 1. And what's 1 over cosine squared theta? Secant squared theta. And that's why the derivative of tangent is secant squared theta, or secant squared x when we're using x as our angle. The other ones could be simplified, could be found the same way. I could rewrite this as cosine over sine, use the product rule. I could rewrite this as 1 over cosine, use the quotient rule. I meant quotient rule there too. So all of these could be found out using the quotient rule. But we are just going to use them now. The sooner you can memorize them, the better. For this first quiz, I will give them to you, but after that, you'll have to memorize them. Okay? All right, so let's go ahead. We're going to be using these new derivative rules. Looking at the first problem, the derivative of 4x is 4 plus 2. The derivative of cotangent x, well, here's our derivative. It's going to be negative cosecant squared. So I'm going to have times negative cosecant squared. What I see people do here is they say, okay, this is 4 plus 2 minus cosecant squared x. That's not right. This is positive 2 times negative cosecant squared. So this is going to be 4 minus 2 cosecant squared x. That's going to be that derivative. For the next problem, 1 over x. How can we rewrite 1 over x? X to the negative 1. So simplifying this has been done. Now I have to take the derivative. 1 times negative 1 is negative 1, x to the negative 2, minus, I look at my derivative of cosecant. The derivative is negative, and I already had subtraction, so if I have a negative times a negative, that's going to be a positive. This coefficient just gets carried down. So it's plus 5, and then I just write this derivative. Whenever we have a coefficient on a trig function, we just carry it down. Now I should get rid of this negative exponent, so a better answer would be negative 1 over x squared plus 5 cosecant x cotangent x. For example 3, here we have just two terms that we're going to take the derivative of. So the derivative of 3x is 3 minus, bring down the coefficient. What's the derivative of tangent x? Secant squared. So I'm going to have this. When I'm left with something that has a common factor, I should see if I can simplify by factoring out that 3. I'm going to be left with 1 minus secant squared x. Well, if I go back up here to my Pythagorean identities, 1 minus secant squared x isn't going to be tangent, but it's going to be what? Negative tangent. So a better answer for this would be negative 3 tangent squared x. So when you check your answers on this homework, you're going to want to look at those and make sure that you get it completely simplified. All right, let's look at example 4. G prime. Now, what am I going to have to use on this one? See, on this one, I just took the derivative of the first term and the derivative of the second term. But these are factors. So what am I going to have to use here? Product rule. I have to do f prime g plus f g prime. So the derivative of secant is secant tan. This is an okay answer, but to make it even better, I'm going to factor out an x secant x. So if I take an x secant x out of the first term, I'm just left with 2. When I take an x secant x out of the second term, I'm left with an x tangent x. No, we're using the product rule. So the product rule is f prime g plus f g prime. If it had been a quotient, we'd use subtraction. All right, let's go on down to this last one. Determine the point or points at which the graph has a horizontal tangent line. We've done this kind of problem before. Does anybody remember what to do on this kind of problem? So we have some function. We don't know exactly what the function looks like. Maybe it looks something like this. I don't know what it looks like, but we want to know, where do we have a horizontal tangent line? Yeah, exactly. We want to find the derivative, set it equal to 0. Very good. So what rule am I going to use to find the derivative of this? Product or quotient? Quotient. So quotient is the f prime g minus fg prime over g squared. So let's do that. So f prime is 2x times g minus f times g prime all over g squared. Now, I'm going to have to, you guys said, when I'm asked for where do we have a horizontal tangent line, I think what's the slope of a horizontal tangent line? It's 0. So I have to set my slope, my derivative, equal to 0. Well, if I cross multiply here, it's going to be difficult to solve unless I simplify first. That's why we simplify. So we're going to have to simplify this. This is going to go down to 2x cubed plus 2x minus 2x cubed. Now look at this, guys. What's this going to be? Now I have negative times negative 1 times 2x. Positive 2x. So now simplifying this, I think you guys are thinking ahead, right? This will be 0. But this is going to be 4x. So there's my simplified derivative. I'm going to set that equal to 0. We're going to cross multiply. We get 4x equals 0. So therefore, x equals 0. So our point then is going to be 0. Plug it back in. 0 squared is 0 minus 1. It's going to be negative 1. And that's going to be the only place where we have a horizontal tangent. I just want to take a look at it just to see what the function looks like. So here's what the function looks like, and we want to see at 0, negative 1, does it appear we have a horizontal tangent? There's 0, negative 1, and see that graph didn't look anything like we were thinking. And this couldn't be right now that I think about it, because in order for it to look like this, we'd have to have vertical asymptotes, and we don't have any, because that denominator would never equal 0. So that is not at all what it looks like. It looks like this, and that's why calculus is so helpful. Because we can, even without knowing what the graph looks like, we can still tell where we have the horizontal tangent. And now I could check and say, what is that slope right there when x is 0? And it tells me the slope right there is 0. And that's the only place. Okay? All right, questions? All right, guys. Let's go ahead and work on that second assignment.